So today is 15, yeah? Of February 2024. So I would like to recall that we have started investigation of neutrino mixing and oscillations in the presence of external electromagnetic fields. This is a very important issue related to neutrino electromagnetic properties, which are the main subject of this our set of lectures. Yeah? So I would like to recall what you for sure know. So if we consider the case that the mass of neutrino is not zero, this is beyond the standard model. There are a lot of different theoretical frameworks that go beyond the standard model. Because in the standard model, it is supposed, it is fixed, that the mass of neutrino is zero. But you know from the previous half a year of our meetings that it is proven experimentally, we can say it like this, that the mass is not zero. Because in other words, if the mass is zero, there is no mixing and no oscillation, and there is no chance to explain the observed neutrino fluxes in experiments from the sun and from atmosphere. And there are a lot of other experimental verifications of the fact that indeed neutrinos has non-zero masses. So the present status of the mass of neutrino, as we have discussed with you, that the mass of neutrino. So there are three different mass states and three different neutrino flavor states, which are each of these the superposition of these mass states. And from experimental results, we know that at least two of three masses of mass states of neutrinos, at least two are non-zero. So two are not zero, and there are no two with equal masses, because we have to explain separately with the experiments with the solar neutrinos and with atmospheric neutrinos. And if you remember, different mass square differences are used, not zero. And if you have three masses, so just a consequence that there are two, at least two not zero, and in addition they are not equal to each other. So two not zero and not equal masses. Yeah? Only one mass can be zero. And the rest two are not equal to each other. Yeah? Okay, this is the status. So if, and of course these experimental results force us to go beyond the standard model describing neutrinos. It's inevitably. It's an experimentally proven fact. Yeah? The most important. So we should go beyond the standard model. The standard model. And if we just consider the easiest generalization of the standard model, just using the same Lagrangian as in the standard model, plus we add a singlet right-handed neutrino state to have the mass term in the Lagrangian. So we immediately, if we do not change reasonably the theory, so it means that in the limit of switching of masses, we should go back to the standard model. So it means that all interactions that exist in the standard model should be described with the new theory beyond the standard model. And if so, there are contributions to the neutrino magnetic moment. This is magnetic moment of neutrino. magnetic moment of neutrino from this kind of diagrams. One loop, this is the mass state, this is mass state, this is the mixing matrix, and this is W, and this is electron, muon, or tau, and this is W, and this is again mixing. So we express the mass states in terms of superposition of flavor states, 3, electron, muon, tau, and each of these states should interact with W boson. And if we couple here the photon or here, we get immediately that the neutrino magnetic moment in the mass basis, is proportional to the masses of neutrinos. I just wrote this expression. Yeah? This is just a result of one loop diagram calculation. This is reasonable, and it is not possible to switch it and to wash out this effect. Okay? So, the result of this discussion and consideration is the following, if the summary makes summary. Massive neutrinos should have non-zero magnetic moments. Okay. Of course, we can go to another series, more sophisticated, more general, just include new interactions, but they cannot switch off these that have an image in the limit of mass to zero in the standard model. Okay. Now, we should deal and start, and I would like to start, with the equation that describes neutrino motion in an external electromagnetic field, accounting for the fact that neutrino has non-zero magnetic moment. That today I will give a kind of introduction or supplement material to the line that we started in the previous lecture. Also, I hope that our colleagues will join us, and we shall continue what I have started a week ago. But today it is very important for our motion in the direction of describing more general case, when we just include not only electromagnetic fields but also matter, which can move in respect to direction of neutrino propagation. So, and we discussed many interesting effects related also to the interaction of neutrinos with the moving matter. This is one of the very spectacular effects. So I have mentioned that in the presence of transversal magnetic field, a new type of mixing and oscillations appear between left and right-handed neutrinos. But in our paper we have discovered about 20 years ago that it is a real new effect, that the spin mixing of spin states and corresponding oscillations can be produced without any electromagnetic properties, without magnetic moment, without presence of external electromagnetic or magnetic field, but due to weak interactions of neutrinos with moving matter, if the transversal component of the flux of matter exists. So, and we have shown that spin oscillations can be produced in case when neutrino is propagating inside moving matter, and when there is a transversal current of matter acting on neutrinos and produce also spin flip. This is a very interesting phenomena that can have important consequences in astrophysics. I have just proposed this effect in 2004. Then, about 10 years later, together with my student Pustoshny, we just calculate many interesting effects that is just straightforward from this prediction. And then other people start using this for the analysis of astrophysical fluxes in extreme environments when there are very dense matter moving with high velocities, also with the transversal components in respect to neutrino propagation. But all this will be discussed during the forthcoming lectures. But now I would like to start with the most simple case, tutorial I should say in a sense, but it will help us to go further in describing more complicated phenomena related to electromagnetic properties and not only. So let's start as if we fix this fact that massive neutrinos should have non-zero magnetic moment. Let's start with the effective equation of motion of this neutrino. It is like a Dirac equation for electrically neutral particle, but which has non-zero magnetic moment. This is very well known Pauli generalization of the Dirac equation. Please, yeah, okay. You just come exactly in time. Okay. This equation is called a Dirac-Pauli equation. You know from quantum electrodynamics. This is equation that describes, in the case of electron, accounting for anomalous magnetic moment of electron. Yeah, in case of neutrinos, if we do not consider the case where the neutrino can be merely charged particle, but this is also very interesting phenomena that we discussed, and in our group we spent a lot of efforts in studying effects of neutrino merely charge, electrical merely charge. But now we fixed the situation that neutrino is not charged particle. The charge, merely charge or charge of electric charge of neutrino is zero, but nevertheless, if neutrino is a massive particle, it has non-zero magnetic moment. This is anomalous magnetic moment, because the normal magnetic moment, as you know from the Dirac equation for electron, just comes, is related to, is described in a sense by the non-zero charge. Yeah, but the diagram I just showed before, it gives contribution to magnetic, additional part to magnetic moment that is called anomalous magnetic moment. But in case of not charged electrically charged neutrinos, people used to skip this word. This they call this magnetic moment of neutrino, but really this is an anomalous magnetic moment of neutrino. Yeah. Okay. So we start with effective Dirac-Pauli equation. Pauli equation for a neutrino. Yeah. So the wave function of in an external electromagnetic field given by F mu tensor, yeah, of electromagnetic field. So this is I, the Dirac matrices. This is derivative, the summation over mu plus minus mi. This is the mass of the mass state of neutrino plus 1/2 the magnetic moment of the mass state. So we start the most direct and proper way to introduce electromagnetic properties for the mass states of neutrinos in the mass basis. Yeah. So, of course, by mixing, we can transfer or just can move electromagnetic characteristics and calculate or determine them in the flavor basis. There will be a superposition that will be determined by the mixing matrix, elements of the mixing matrix, and I will show these formulas exactly. But the most correct way and most easily be accepted to understand the phenomena, well, you have a particle, you have a mass of the particle, and just in this basis, in the mass state basis, you introduce electromagnetic properties. So this is the magnetic moment in the mass states of neutrino. But if you consider in many experiments and also in astrophysics, if you are studying or just observing, are going to describe electromagnetic properties, you detect flavor neutrinos in experiments, because you interact neutrinos by interaction, but flavor neutrinos, we know how flavor neutrinos interact with, well, to say, we are not, it is, of course we can make transition from the flavor to mass states, but Lagrangian interaction is determined in terms of flavor neutrinos. And of course, most of experiments deals with the flavor neutrinos. Also in astrophysics, neutrinos interact like a flavor states, yeah, with other particles, with neutrons, protons, etc. And then if we are interested in a manifestation of electromagnetic properties, we should turn from the mass state defined characteristics, electromagnetic to the flavor. There will be effective magnetic moments for electron neutrino, for muon neutrino, etc. And they will expressed as superposition of the magnetic moments, if you are considering particular magnetic moments, as a superposition of different magnetic moments determined for the mass states of neutrino. But now we are considering equation, Dirac-Pauli equation. This is the mass of the mass state of neutrino in the mass state. Yeah. So this is the magnetic moment for the massive neutrino. Sigma mu nu, f mu nu, and here this the wave function of the flavor state of neutrino. X is the coordinate. This is the well-known Dirac-Pauli equation that accounts for anomalous magnetic moment of, in our case, of neutrino. So I just recall F mu nu is the combination of Dirac matrices like this. Of course, it's very common, and you know this. Well, we are interested in the case when magnetic this tensor is just a constant magnetic field. Constant magnetic field. So we shall consider this particular case. However, just in one of the next lectures, we consider more general problem of neutrino mixing oscillations in arbitrary electromagnetic fields, including the case of the electromagnetic field of the electromagnetic wave. Also, we shall discuss, and this is one of the important new effects that was discovered and considered in our papers with my students. So I have to put plus or plus, yeah? Okay. So this equation can be derived in the momentum space. Yeah, that equation was in the coordinate space. If you make the Fourier transform of this, and we get the following gamma momentum. This is, of course, the sum like this, minus the mass of neutrino plus magnetic moment of neutrino divided by 2, the same sigma mu nu f mu nu, and here this the wave function in momentum space. Yeah, So it is like completeness, just like this. Now let's consider the case of the constant magnetic field that is determined by its projections to some fixed axis. Yeah, these components of the vector of magnetic field. So then, if we just consider this decomposition, so we can write an exact expression for the tensor of electromagnetic fields and just fix all the components of this tensor. Yeah? This 4x4 matrix. There is no electric field, yeah? Only magnetic component. 0, 0, 0, 0. Then 0 again, 0. Here is minus the third component of magnetic field, plus the second component of magnetic field, 0 plus the third component of magnetic field, 0 minus the first component of magnetic field, 0 minus the second component of magnetic field, then plus the first component, 0. This is the tensor of electromagnetic field for the particular case of the constant magnetic field given by its component. We fix the axis, yeah, and projections of the field. So now it is quite easy now if you know the properties of these matrices. It is very easy to calculate this term. We can easily calculate this term and express it exactly in terms of the projections of the constant magnetic field on the fixed axis of the reference frame we fix. So then we can write that this magnetic moment, I just skip, I will not write further this I, obviously. It's I divided by 2. This is sigma mu nu f mu nu equals to I mu. And here I just use an exact form of this tensor for our particular case. This is sigma 2 1 b3 plus sigma 1 3 b2 plus sigma 3 2 b1. And this can be written in the form minus mu sigma vector b vector, where we use this matrix 0, 0, 4-component matrix. This is just the properties of these gammas, and this is sigma mu nu. Yeah. I recall Pauli matrices. So sigma 0, this is unit matrix. We use them. Of course, you remember, of diagonal, sigma 1, sigma 2 with the minus I 0, and sigma 3, we use them exact expressions, minus 1. This is Pauli matrices. Okay, now we are ready to start determining or fixing the problem. So we would like to derive an effective Hamiltonian for the mass states of neutrinos that will describe neutrino propagation in vacuum first, accounting for the magnetic moment interaction of neutrinos with a constant magnetic field. So, and we can just announce that we start the problem of neutrino I say evolution in a constant magnetic field that have two components in respect to neutrino propagation. So we consider the case that neutrino is moving and there is a constant magnetic field that is described by two components, B longitudinal, the component of the magnetic field alone to neutrino propagation, alone to neutrino momentum, and the transversal, it's the magnetic field transversal perpendicular to neutrino propagation that is given by the vector of momentum of neutrino. And what we would like to have? We would like to find an effective equation of evolution of the mass states of neutrinos in vacuum, accounting to magnetic moment interaction to this magnetic field. So we would like to find something, the effective Lagrangian, Hamiltonian of mass states of neutrino in magnetic field. If we switch off a magnetic field, we know for the mass states of neutrinos what is the effective Lagrangian. If the field is zero, in case magnetic field is zero, we know this effective Hamiltonian is just energy, 0, 0, neutrino energy, and alpha equal 1 or 2. We consider two mass states of neutrinos. Yeah? We know that this is like this. And here I put like this, and we expect and can guess that in case of the presence of and interaction of neutrinos with a magnetic field due to non-zero magnetic moment, an additional term will appear, plus, let's call it B, or mu B, as you wish, B in magnetic field, or mu B, yeah? And we are interested in this guy. So we'd like to find an addition or a shift on effective evolution Hamiltonian for our mass states of neutrinos, accounting and appear due to electromagnetic interaction with the magnetic field. Sorry. Okay, how to start this problem? I think that you will agree with me that this effective Hamiltonian sorry, is equal to minus 1/2. It's come from Lagrangian of neutrino interaction with the magnetic field. And Lagrangian comes from the Dirac-Pauli equation for the mass states of neutrino with non-zero magnetic moment in magnetic field. So we can postulate an equation, then we know what is the corresponding Lagrangian. Or, in other words, you can start with Lagrangian and then derive this equation, yeah? And this depends. What is your choice, yeah? And knowing the Lagrangian, we can understand what will be the structure of the effective Hamiltonian of neutrino evolution, accounting for this particular interaction. So this is, I just put, so this is, if you know Lagrangian, you can write the corresponding Hamiltonian. And I will just put this letter like this. This is not an evolution Hamiltonian that enters the neutrino evolution Schrödinger equation. This is the Hamiltonian that corresponds to this Lagrangian. It's the same. Yeah, you know the sign is different. Yes, Lagrangian, Hamiltonian is if there is no derivatives over the fields, they are related with the minus sign, Hamiltonians and Lagrangians. Okay, so this Hamiltonian is just, we have discussed already. This is magnetic moment, nu bar sigma mu nu, nu f mu nu plus Hermitian conjugate. Yeah. Now, for the further needs, I would like to introduce more complicated electromagnetic property, possible that probably exist in nature. It's not excluded. That in this electromagnetic interaction of neutrinos with an external electromagnetic fields, and the particular magnetic field, it may happen, and in some theories it can be included, that not only electromagnetic interaction is described, but also it can be that the type of neutrino is changing. So it means that I will put here 1 and here 2. So it means that in electromagnetic interaction with magnetic moment, also the type, the mass state of neutrino is changing. So this looks very much like a magnetic moment interaction, but in addition, the mass state neutrino 1 is transferred to the mass state neutrino 2. And this can be the case, and this possibility is not excluded by the experimental results. Because in many experiments where we study in trying to measure the magnetic moments, from theoretical point of view, diagonal and possible not diagonal neutrino magnetic moments enters to the values that can be checked in experiment. And you cannot distinguish which, if you see the effect, you cannot distinguish which of the type of magnetic moments give really contribution, whether diagonal or off diagonal. Often in these experiments, and we shall discuss this, an effective magnetic moment is verifying and constrained, where there are contributions from the diagonal and off diagonal magnetic moments that are a mixture, so you cannot distinguish. Yeah? So in this case, we have to distinguish. This is not a magnetic moment of neutrino 1 or neutrino 2. This is a transition magnetic moment. This is a transition magnetic moment of diagonal. So this is transition, not diagonal. of magnetic moment. Transition or magnetic moment. This is for the most general case. Now, okay. So we consider I, this is a neutrino of mass state I, magnetic moment. And this is not equal I. This is transition magnetic moment. No, sometimes in this case moment is missing. Transition moment magnetic is missing. Moment of neutrino. Of course, interaction, electromagnetic interaction, being together different mass states in this case. Yeah? Okay. And what about the effective contribution or effective Hamiltonian, the effective contribution to the effective Hamiltonian of neutrino evolution that enters the Schrödinger-like evolution equation for our neutrino system. We shall determine it in the following way. So we consider, so we have to calculate the kind of energy contribution, yeah? Because Hamiltonian is determined by the energy, yeah? Electromagnetic interaction shifts, gives an addition to the energy. So, and we determine the additional term to the evolution Hamiltonian, not this one that is one-to-one related to the Lagrangian of interaction, but this is evolution Hamiltonian. We have to make an average of this real Hamiltonian for a particular between different states that are connected by this Lagrangian or Hamiltonian. So we have to calculate the following. This is nu1. This is Hamiltonian that comes, a real Hamiltonian of interaction, B, and this is nu2. So we have to calculate all these terms. We have to calculate, and that will give a contributions to the effective evolution Hamiltonian that we then shall use to formulate, to settle a problem of neutrino mixing and oscillations in the presence of, for the case of non-zero magnetic moment, in the presence of the external field, but we choose now for, as an example, the field to be the constant magnetic field. So we have to calculate this kind of terms. Let's start making this, realizing this project. Yeah. So neutrino state. We use an exact neutrino state, nu1, that is corresponds to the mass, to the momentum, and to the energy. We use this as a solution of the vacuum Dirac equation. Yeah? Some constant, normalizing constant, then the square root, the energy, plus the mass, divided by two energies. And here, U1 sigma pair 1, this is vector, divided by energy plus m U1. And the exponential part, I minus energy over time plus the vector of momentum and the vector of the coordinate. This is a vacuum solution for the mass state of neutrino that is determined, this is characterized by the mass, energy, and momentum. Yeah? Normalized solution of the corresponding Dirac equation. Yeah? So then for the second mass state, we have the same, only just we change the indices from 1 to 2. This is momentum, this is the energy, this is some constant that are really not important for us in our calculations. Energy plus mass divided by 2 energies. And here we put U2 sigma momentum divided by energy with the corresponding index that should be U2, exponent I, energy multiplied by time, corresponding momentum multiplied by the coordinate. This is a vacuum solutions for neutrino of mass 1 and the mass state of mass 2. And we should calculate once again the average. And then we just get a typical energy related to transition between different neutrino states. Yeah? By definition, this is using the exact expression for this Hamiltonian that is determined by the Lagrangian of magnetic moment interaction of particular neutrino mass state with external magnetic field. This is minus divided by 1 by 2, the integral over space and time, nu 1 cross gamma 0 sigma multiplied by the strength of magnetic field vectors 0, 0, sigma b nu 2. So just here, by these terms, we count the spin states of neutrinos. Yeah? Spin states of neutrinos.
Energy in the second equation for.
Sorry?
Energy with minus should be.
Yeah, of course, yes. Yeah, and of course, yes, thank you. And also, I just skip here. I just skip here. No, I just put everything. Yeah, okay, minus, yeah. So to describe the spin states of neutrinos, we just agree. We agree that U alpha, where alpha can be equal 1 or 2, and add an additional characteristics that describes the spin state. Sometimes you can put 1 or plus or minus. I put 1/2 and minus 1/2, and this is 1, 0 for both, for alpha equal to 1 or 2, yeah? And another spin state, again, that corresponds to the opposite spin orientation, equals to 0, 1. So we just introduce also the spin characteristics, yeah? So it means that we deal with two mass states neutrinos, each in two possible spin states. In general, our evolution Hamiltonian for our neutrino complex, let's say, will be 4×4 matrix, yeah? 4×4. So we deal with 4 different states. They differ from the mass values, different 2 masses, and each have 2 possible spin orientations. Understand? Yeah. So it means that we have to calculate 4×4 these terms, and we should calculate, and then we shall add to the vacuum Hamiltonian, or effective Hamiltonian in vacuum. Yeah, this is our goal. Now let's start making these calculations. Okay. The starting point is the following: 1/2 mu 1, 2, the integral over space and time, I just put here a vector B, 3-dimensional vector, then U1 cross sigma P1 divided by energy of the first and plus mass of the first, U1. Then this is a matrix sigma 0, 0, sigma. I just put this magnetic field, this is just a vector, this is not a matrix. I just put from here, because then we shall make manipulations with these sigma matrices, yeah? Because you just can easily just move this vector to this position. Well, this is a matrix. This is also a matrix. Yeah, it's 2×2. Yeah. This is 2×2 matrix with zeros. Yeah, understand? Yeah? And this is just a common vector. Yeah, understand? So, and then we put the second neutrino here that is described by U2, and the same as it was for the first neutrino, the momentum, second, divided by energy plus the mass of this neutrino. Okay? And also should be multiplied by the exponent I minus delta energy multiplied by time plus delta momentum multiply x, and everything should be multiplied by the general term E1 plus M1, E2 plus M2, square root divided by 2, square root of energies E1 multiplied by E2. Okay? So, and we have to calculate this. This is a typical term. And once we calculate it for one particular case, we then generalize this and can easily reproduce all terms in effective evolution, additions to the effective evolution Hamiltonian that is 4x4 matrix. Yeah? 4x4, once again, because there are two mass states and two spin states. Yeah? In general, it's 4x4 matrix. Yeah? Okay. And we shall calculate for particular choice of these indices and then generalize it for other terms of this evolution Hamiltonian. I would like to say that this, what is here, this delta E is E2 minus E1, and delta momentum is momentum 2 minus P1. So this term just can be switched off, can be cancelled out due to renormalization. It will give volume and time. Yeah, so it is not important for us, and I will show you probably next time. Okay, let's start making these calculations. So let's fix the reference frame in the following way. So we fix 3 orthogonal axes, and z, this unit vector, and y, and nx. Yeah. So this is alpha, and this is the vector of the magnetic field, and we suppose, without loss of generality, that neutrinos are moving both states along nz, and that is along the longitudinal component of a magnetic field. Yeah. Okay. Now let's start making these calculations. So we have to examine the following terms just from this expression. So we have to calculate U1 cross B vector sigma vector U2 minus U1 cross sigma P1 sigma B sigma P2. So we just should examine the typical terms here just to evaluate further. Here I should put also U2, yeah, not missing this, and also the denominator E1 plus M1, E2 plus M2. Okay? Yeah, this is 1, this 2, 1, and 2. Okay. So this is not, this is more or less obvious. Well, I would like to help you to understand what this guy is, yeah? And recall a very important formula, probably you know this, sigma A vector multiplied by sigma B vector, constant vector, equals to the product of two vectors A and B plus I multiplied by sigma and then A vector B vector. This is, probably you know this expression, yeah? This is the properties of these sigma matrices, yeah? Okay. And we just apply this to simplify the nominator of the second term. Well, and we can just using this, we can go further, plus, and we can get that this is equal to U1 cross bracket sigma the longitudinal part of probably I will probably I will can write just the final form 1 minus P1 P2. This is the product of vectors, yeah? Divided by E1 plus M1, E2 plus M2, plus sigma, the vector of the transversal magnetic field, yeah? We just decompose to two vectors and treat them separately, yeah? 1 plus P1 P2 divided by E1 plus M1, E2 plus M2. U2. Okay? Do you understand? Yeah, it's okay? No, I would like to ask you to check it, yeah? Okay. So we should consider four combinations. That help us to write the final solution, yeah? So the first combination, I just write it as S plus minus. So there is a change of spin orientation, yeah? Understand, yeah? Okay. So, and in this case, we shall deal with this term U cross 1 without change, plus plus, yeah? U1 S equals to 1/2 sigma vector B U2 S equal to 1/2. So just this is 1, 0, sigma 1, 0, B longitudinal plus B transversal. And if we agree that longitudinal equal to B cos I alpha and B transversal equals to B sine alpha, this is, we just make a projection, yeah? Then it will give the result B cosine alpha. B cosine alpha, yeah? And then there is the second option that we describe like this. There is a change from plus to minus of spin orientation. Then there is the third one, S, when from minus to plus, and the fourth one from minus to minus. And I would like to ask you to calculate yourself. Yeah? And probably under the pressure we shall stop.